All right, so 4.3. Hopefully you did 4.1. Hopefully you read 4.2, because that sort of got the basis for the rest of it here. So 4.1 was something about exponential functions, is that right? How to graph them, how to look at them. 4.2 was an introduction to logarithmic functions. Again, how to graph them. Very, very elementary properties of log functions here. So 4.3, 4.4 sort of finish it off with all the stuff we should be doing with them here. So we're going to look at the rules for them, and then we're going to use those properties to simplify. And eventually 4.4, we want to be able to solve equations, because that's really what we want to get to. Okay, just quick show of hands. How many have seen exponential logarithmic functions in algebra? Just out of show of hands here. How many seen it? Maybe. Okay, about 20% of you. Okay, so try to keep up. Ask the questions if you need it. Okay, I'd rather it make sense than not make sense here. So let's go for it. So rules for logarithms. That's what we're going to cover first, and then a quick little example problem, how to estimate large numbers real quick here. That's kind of fun. And then we're going to look at the change of base formula, and then we're probably going to skip the growth and decay for now, just so we can get through both sections here. But here's some rules here. First rule of logs: if you have two numbers that are being multiplied together inside the log, what you can do is you can split them off, but you can split them off with a plus sign. All right, and hopefully you've sort of understood to say, Mr. H, you know what, aren't logs really just exponents? And that's exactly right. Logs are just exponents. And so if you remember this little rule from algebra, let's go b to the m times b to the n. Anybody finish this off from algebra?
M plus n.
Perfect, yep. Remember, this is the product rule for exponents. If you're multiplying two numbers, all you're going to do is add the exponents. Well, the logs are exponents. So notice you got a multiplication between the m and the n. And so what happens is you got yourself a addition of the exponents. Because whenever you take a log of something, you're saying what exponent makes that true. Just real quickly here, just so we know, for those of you that might not have read 4.1, what's the answer to this?
Isn't it 3?
What exponent do you put on 2 in order to make an 8?
3.
It'd be 3. So notice 3 is actually an exponent. We good? Logs are exponents.
Oh, I read it.
Okay, no problem. Okay, rule number 1. Let's go with rule number 2. If you're dividing two things, all you got to do is subtract exponents or subtract logs. Okay, which one does that correspond to? I think it corresponds to this right here, right? B to the m divided by b to the n. So dividing two numbers, all that means is you just subtract the exponents. Yes, these properties are important because we use them to solve equations later on. So yes, very important stuff. Okay, next one. The power rule here. Log base a of m to the r power. The exponent to the number becomes the multiplier to the number itself. All right, what rule does that correspond to? I think it's this one right here. B to the m to the n power. Notice what we're doing is we're taking a power of a number called b to the m, but really all we got to do with the exponents is just multiply the exponents. That's exactly what it means. This is r is now multiplying that log. Okay, so here's the first three. We'll get to a few more. All right, so let's work with these just to make sure we got them here. So again, this is just to make sure that you understand. Let me just look at A and B maybe, and C. So we'll look at them here. So let's say log base 5 of Z is equal to 3. Log base 5 of Y is equal to 2. What we want to do is we want to be able to break up A somehow so that we get in terms of these two logs. And once we have in terms of these two logs, then we can evaluate them based upon those numbers. And those numbers are arbitrary. Again, you're just playing with it to make sure you understand the rules. Cool. So two numbers are multiplying inside. What they get to do, they get to be the addition outside of the log. So good. Split them off as addition, and then you say, oh, you know, I know that. That's going to be 2. That's going to be 3, and the grand total is 5. Again, completely arbitrary. You're just playing to make sure you understand the rules. Okay, with B, let's take a look at B here real quick. Log base 5, again, not doing anything. You're just paying attention if you want to. Notice you got 125 times y to the 7th. Hey, if it's y to the 7th, I can bring that out. Actually, there's a multiplier here, right? So I can split them off as a plus sign. I don't have a 5 yet, but I know that 125 is really 5 to the 3rd power. This little 7, that's the exponent, this actually can be brought in front. That's the little product rule that we just looked at, the power rule. Okay, and this one you should know from previous sections here. So log base 5 of 5. So what exponent do you put on 5 to give you 5 to the 3rd? Obviously, it's that 3 right there, right? And then you got the 7 coming in from here, and log base 5 of y, that's given to us as a 2. So grand total is 17. We good? Again, just playing just to make sure you understand how you get what you need to get. Let's go through these just to make sure. We have a square root on our hands. Remember, a square root is really a half power. That 1/2 power gets to go out in front because the power rule again in front. And then the z divided by y, that can be a subtraction between two logs. Good there? But you have to put in parentheses here because you got two terms here. So now in light of that, then we say, okay, that means that's 3 minus 2. That's a 1, 1 times a half. I think the next one, let me do just D just real quickly here. Log base 5 of z to the 1/30th times y to the 5th. So that means I could split this off into two different things that are multiplying each other. The 1/30th gets to go out in front because it's a product rule. The 5 gets to go out in front because it's a product rule. And then this is given as a 3. Again, this is given as a 2. That's going to be 1/10 plus 10 gives you 10.1. Are we good? Again, just playing just to make sure you understand how to do it. So all yours then. Can you simplify that just to a single number? Or use the properties of logs to simplify that to a certain number?
So y is still equal to 1, 2?
Yes, Question is, does log base 5 of y, yep, log base 5 of y is equal to a 2. Log base 5 of z is equal to a 3. Let me get to you in different, no, I'll wait. All right, here's what I got. See if you guys agree here. So log base 5 of y divided by z becomes log base 5 of y minus log base 5 of z. Good there. And then according to the rules here from the book, that becomes 3 or 2 minus 3, which gives you a -1. We good? Maybe. And again, just making sure you know the properties here. So split them off because the division makes a minus sign and then plug in the values. Okay, this one. There's a multiplication here, so that means I could split it off with a plus sign this time. So it's log base 5 of y squared plus log base 5 of z to the third. Can't simplify it yet. I got to take this 2 on the y, bring it out in front as a product. So bring it out in front. That's going to be 2 log 5 of y. Same thing here. The 3 goes out in front as a 3 log 5 of z. Now I can simplify it. Anybody with an answer? I heard that. 13 is good, yep. It's going to be 2 times 2 over here because of the definition, plus 3 times 3 because of the other definition, and eventually 4 plus 9 is 13. Okay, good there. Properties there, just making sure we understand them here. Let's go just a little bit more complicated now. This is what we really do when we look at equations here. Any questions from Kalinga? Going once, going twice? Thought there was somebody. Okay, let's look at example problem first here. Okay, gets a little more complicated. So this is just an example. Log base 2. What I want to do is I want to expand this out as much as possible. Whole bunch of stuff here. Look at this. There's a product right here. Is that right? There's also a division here. So we normally we do the division first here. So x squared parentheses x minus 1 to the third divided by 2x plus 1 to the fourth. Because there's a quotient here, separate it by a minus sign. Everybody good there? Now you got a product between x squared and x minus 1 to the third. There's a product there. So I'm going to separate that out as a plus sign. So notice I have 3 different terms now. And then I'm going to take my exponents, put them out as products in front. So that 2 goes in front, 2 log base 2 of x. That 3 goes out in front. And notice when you need to use parentheses, you want to use parentheses to hold that binomial still in place, because you're saying log base 2 of the quantity of x minus 1. Good there? All right, that 4 also does the same. 4 goes out in front. And then again, whatever's left over, still keep the binomial as a term of the log. Cool. So log base 2 of 2x plus 1. All right, of course, easy one, and then a more difficult one. It's always fun to do it that way. So here's yours. Practice problem number 2. I let you deal with the B for a little bit, but A's should be pretty easy. All right, let's go for it here. So first one, ln. Now, real quick here, remind you guys, remember what ln is. Ln is log of base e. And e is a very important number in mathematics because there's a whole bunch of natural sort of applications that come out of it. Chemistry, a whole bunch. Geography, you name it. There's even banking. You got this. So log base e is ln. It's a short way of writing it. So it's called log of the natural number, or natural log. The reason why we say natural log instead of log of the natural, because the French, that's when they sort of put this together here, they always said log of the natural number, so it just became ln. So real quick here with A, notice there's a quotient here, so in order to undo the quotient we're going to do subtraction. So ln of 2x minus 1, you got to put in those parentheses now because you're grabbing that 2x minus 1 inside that ln. Cool. No exponents to put outside, so we're good to go there. Okay, B gets a little tricky here. If you did B, you did good. So first things first, you got that square root to deal with. Square root is really a exponent of 1/2. So in this case, everybody agreed with that? That 1/2 has to go to the outside, so I got 1/2 of log of 4x over z. Okay, once you split this off, though, we got ourselves in trouble because this is one term. We're taking half of this single term. When you split it off, now it becomes two terms. You have to put in those extra parentheses now because you are splitting off that z that was on the bottom. Okay, going some more here. I see products here. I got multiplication between the 4, the x, and the y. I'm going to split all those off. So 4 goes by itself, so 1/2 of the ln of 4 plus the ln of x plus the ln of y minus ln of, sorry, not ln, sorry, log. Log of 4, log of x, log of y, and minus log of z. Okay, and again, they want you simplified as much as you possibly can. So 4, isn't that a perfect square still? Yeah, it's 2 squared, right? So they want you to take out any exponents you can find. In this case, yeah, we found some. This is actually log of 2 squared plus log of x. Sorry for making you rewrite all that. Good there. Okay, what happens to the 2, exponent of 2? Bring it to the front, but careful here, it's just going to go right over here, right before the parenthesis, right? Or right after the parenthesis if you're looking at the problem itself. 2 log of 2 plus log of x plus log of y minus log of z. Okay, this is when I run out of space here. So on the bottom, the only thing we have to do is we have to still multiply that 1/2 into each of these pieces here. So half of 2, you're not going to see it quite well here. It's going to be log of 2 plus 1/2 log of x plus 1/2 log of y minus 1/2 log of z. Oh, go back. Okay, everybody good there? It's just sort of so that would be, in a sense, expanded form. You can't simplify anything else inside the log function at all. That's about it. Okay, since we learned one way to do it, let's learn the backwards way. So how about putting it all together? So can we go backwards on these problems here? Can we write it as a single log? So we're going to say log of, we should encompass all that stuff there. So just to give you a quick idea with the easy one here, log of 3x minus log of 4y. If I'm going to put this in condensed form or compact form, we're going to put them together here. So this is log, so I go log of 3x, and then because the minus sign is going to be divided by 4y. We good there? So A should look something like this. So it's really everything in reverse. Exactly what we did, everything in reverse. Again, don't need to write it down unless you really need to here. This one here, you got the 2 on the outside. Any products that are on the outside become exponents inside. So that 2 on the outside now became exponent inside the log. 1/2 now became inside as a exponent of 1/2, which technically is the square root. So I see a plus sign. So putting that all together, that makes it's the ln of x squared times the square root of x squared plus 1. Are we good there? So condensing it down to a single term. Let's try some ourselves here. All right, let's go for it here. Practice problem number 3. So you got a 1/2 on the outside, and it's in brackets, so all this stuff has to be put together. And I see a plus sign. That's what I see. So I'm going to put these two logs together with a plus sign. That means I'm going to multiply this stuff together. So x plus 1 times x minus 1. So let me rewrite it just real quickly here. Keeping the 1/2 on the outside still, this now becomes log of another bracket because it's x plus 1 times x minus 1. Go there, kind of looks a whole bunch of brackets, whole bunch of parentheses here. But you should sort of see this is all part of this log right here. Okay, and hopefully you can multiply this out, right? X plus 1 times x minus 1, what would that be? X squared minus 1, difference of 2 squares. Absolutely. Now it becomes log of x squared minus 1. Okay, simplify that as much as possible. Okay, next is that whole 1/2 on the outside. So the 1/2 now becomes an exponent. And I can even drop the, at this point you can drop the brackets, you don't need them anymore, right? Because you're multiplying a single term. But then you got log of x squared minus 1 in quantity to the power of 1/2. We usually don't like fractional answers. So what tends to happen is if you can't put a square root down, you put it into radical form. And so in this case, final answer would be log of the square root of x squared minus 1. All right. Let me see what time it is. I think we're still okay. All right. This is kind of quick one. Not going to be on the test here, but I just want to show you. Maybe don't even need to write it down. I thought this was interesting. What do you guys say? Big number or small number? Yeah, humongously big number. Is that right? 234 times itself 567 times. So 234 times 234 times 234 times. Whoa, that's huge. Okay, what do we, or how do we write, in what form do we write humongously big numbers in? There you go, scientific notation, right? Remember scientific notation? Humongously large numbers or humongously, or little tiny numbers we write in. So this is what I want to do. I want to write this in scientific notation. We're good? Kind of think with me for a little bit here. So I write down the number, and here's what I'm going to do. I'm going to put a log on both sides of this equation. Again, not going to show up on the test, just want to show this is kind of sort of interesting application. All right, when I get to that, what do I get to do with this 567 now? It gets to be a multiplier, is that right? That's 567 times log of 234. Okay, this actually I can compute on a calculator now. That's actually a fairly small number here. So what I do is I just compute that 557 log of 234 gets me 1343 and some change there. But remember, this is equal to the log of something, right? So this is equal to the log. Log k is equal to 1343. Okay. Good there? So far so good? Okay. Now the question is, how do I get rid of the log? Something that you guys did in 4.2. Just like you can put log into any equations you like on both sides, you have the right to do that. That rule comes from this little rule right over here. You guys remember from algebra? If you have something like this, What can you do there in algebra? As long as the bases are the same, right? You can set the exponents equal to each other, right? Well, same thing here. This is the numbers. These are exponents. Whoop, sorry. These are exponents, right? Logs are exponents. So because we have the numbers equal to each other, I can set the exponents equal to each other. Okay, so then you can also take the exponents out. So what we do is we take 10 over here and 10 over here. We're going to get rid of this here, and that's something you've seen before on 4.1. So then I have something that looks like this. K is equal to 10 times blah, blah, blah. Okay, so what does this mean? This means, see if you guys agree here. Is that right? This is a full set of 10 to the something, and this is the leftovers. So on your calculator, can you now compute 10 to the 0.345391? Think we're good there, is that right? 2.2 about? So it's 10 to the power of 0.345391. Okay. And so there's your answer in scientific notation, which I think is pretty cool. So, and that's a humongous number. That is 2.2 with 1,343 decimals places moved off to the right. I thought it was kind of cool. Okay, we can go on. We can go on. One last thing to do is something called a change of base formula. Notice on your calculator or on your cell phone, you have log, which is log. That is base 10. We call that a common log. And then you have e, or ln, and that is the natural log. Besides that, you have no calculator buttons. There's no log base 2. Now on the TI-84 Plus, if you have that one, now that one does come with log and a certain base, so you can compute that all together here. But normally we don't use those. Most calculators don't have that. So what we've come up with is something called the change of base formula. If you have a log with a certain base and a certain number, what you can do is you can change the to any base which you like. So log base a of x. So you put in the log of the base you like with the x divided by log of the base you like of the previous base. And so usually what we do, again, the two calculator functions you have is base 10, which is this one here. So you go just log of x divided by log of b, or log of the number divided by log of the previous base. It also works for ln, because you can change to any base anyways. So because these are just ratios of each other, it's ln to ln, or log to log, they're going to give you the same answer. So let's kind of quickly demonstrate with the easy one here. If I had log, let's go 5, let's go 100. Before we do that real quick here though, tell me, about what number would this be? What exponent do you put on 5 to give you 100? Close. Going the wrong way. I'm thinking more like 3, is that right? Because remember 5 to the third power is 125. So this number should be just a little bit under 3. 2.7, 2.6, maybe something like that. Okay, now take up your calculators real quickly here and go give me log of 100 divided by log of 5 and see what we get. because you do have the log button, right? Anybody with an answer yet? Sorry, say again. Should be a little under 3, right?
Yeah, 2.86.
2.86. 2.86. Everybody agreed? 2.86. All right. So on the calculator, those of you that like looking funny at your calculators, here it goes. When you press the log button, automatically there's a little parenthesis that opens. That is for your functions. You got to press in the 100. You do have to close this parenthesis off. If you don't, then you're still putting everything into that log function. Then you press divide, then log, and then you're going to, again, as soon as you press the log button, the parenthesis opens up, press 5 and close off that. And that's what you should get. All right, so 2.86, is that right? Okay, how about this? Let's use the ln button. Again, it doesn't really matter. They're just ratios of each other anyways. What do you guys get for that? So ln of 100 divided by ln of 5. Better be the same answer, yeah, because what we just did is use the different button on the calculator, but all we're really doing is looking at the ratio between the two values, and it should be the same. Okay, change of base formula. We'll need it sometimes. Usually we do it to compute something that we don't know. Sometimes we do it to graph things, to graph the ln functions that can be graphed otherwise, or sometimes we just make it look pretty. That's all. So it's not a whole bunch of weird stuff there. All right, quick example here, all yours. Can you find log base 3 of 15? Before you do that, between what two numbers should you find the answer? Yeah, between 2 and 3, right? Because 3 to the second power is 9. 3 to the third power is 27. So it should be somewhere between, probably closer to 2 than to 3. All yours. If you have time, do it both ways. Do it with the log button, then turn around and do it with the ln button. All right, I'm going to try it here. So log base 3 of 15 changes into log of 15 divided by log of 3. Or you could put ln of 15 divided by ln of 3. Because ln occurs so much in nature, maybe about 70% of the time you're going to use ln in calculus, and about 30% of the time you use log, just because the numbers work out differently. But anyways, any which way you chose, you should punch that in the calculator like that. And both ways you should get a 2.46. I just put that. I'm not sure. I think it tells you to put 3 decimal places in the homework here, so that would be it. Okay, there's that. The rest of the section here is just half-life formulas, growth and decay curves, or formulas. They're actually pretty neat to, if you have the extra time to sort of read through. They're pretty fun. Carbon dating, dating King Tut's treasury. That's kind of fun too. But again, if you have the time to read through those, that'd be fun. Let me switch gears and jump to 4.4. All right, so this is the second part of the class here, 4.4. And I'm going to try to finish this. This one will take a little bit longer than the previous one, but hopefully at least give you extra time for questions here. So we've finally come to 4.4, which is being able to solve these things. Now we'll maybe see if we can do an application question. But primarily we want to be able to solve equations. Same thing we're going to do in trigonometry. We're going to learn all this stuff primarily to solve equations. And so let's begin here. So solve exponential equations, solve some applied equations, solve logarithmic equations, and then inequalities, which will be right at the end here, which I think you have 1 or 2 questions on the test from that. All right, let's go for it. Start off very, very easy. We'll work our way to more and more difficult questions as we go. So first of all, I'll give you an example problem here. If you can, this is algebra. This is not pre-calculus here. So going back to algebra, if you can put these both in terms of the same exact base, then you're doing great. 2 times x is 2x, and what we do is we get rid of the base, and what we do is we solve only for the exponents, and you're done. Cool? So if you can get the same base, go for it. Same thing here. 9 is 3 squared, becomes 3 to the 2x, and solve. All yours. So logarithms really come in when you can't put them into the same base. That's when you want to use logs. All right, let's go for it. Anybody found a base for 243?
I got 5.
3 to the 5th, maybe, yeah?
Yeah, 3 to the
Cool.
5th.
All right, yes, it is a base of 3. Kind of careful here. It's not 3 to the 4th because that's 81, but if you multiply one more time, you get 243, which is 3 to the 5th. At this point, easy. X equals 5 is the final answer. Done. This one should be a base of 2, so this is 2 to the 3rd, still to the x power, and this is 2 squared. So when you do this, this becomes 3x as the exponent. The bases drop off, and you get 3x equals to 2 divided by 3, and there's your 2/3. The easy stuff, of course. All right, next one, what happens if you can't find the exact same base? That's what really logs and exponential functions are all about, particularly logs though. So let me look at an example from the textbook here real quick. You got 5 times 2 to the x minus 3 is equal to 17. So what we want to do is we want to get this exponential expression all by itself. So let's divide by 5. And you can convert it to a decimal if you like. But here's our problem. This x is stuck in the exponent. 3.4 would never be a base of 2. And so what we do is we stick a ln on both sides, or a log, whatever you like. And we got some rules here. What happens to the exponent inside the log? It's the power rule, right? It gets to go out, right? So now it becomes x minus 3 times ln of 2. In that case, let's distribute over here, so that becomes x ln of 2. Or even divide it out, sorry. I divided it out. Divide by ln of 2. Add 3 to both sides, and there's your answer. I'd probably distribute everything out and solve for x. Okay, we good there? So there's a way to do it. I'll let you guys try the next one here. Go for it. So 7 times 3 to the x plus 1 equal to 11. All right, those are waiting for me. Let's go for it together here. So first things first, I'm going to divide both sides by 11. I'm sorry, by 7. Cool. 7 goes away from the right-hand side, so I got 3 to the x plus 1 is equal to 11 sevenths. This one I really don't want to convert to a decimal because it's going to be a decimal forever. So I don't think so. I'm going to keep it just like that. Alright, but he's got that x stuck in the exponent there. That's the problem. So let's take ln of both sides. So ln of 3 to the x plus 1 and ln of 11 sevenths. Alright, got this little rule called the power rule. Very important. Look at this, x plus 1 now gets to become the multiplier in front is x plus 1 times ln of 3 equal to ln of 11 sevenths. So we're good there. Sweet. Okay. At this point, kind of depending on what you want to do, I prefer getting rid of decimals, of course, and then moving our way through. So I would probably I would probably multiply through the ln of 3 because we're always taught to get rid of parentheses by distribution here. So ln of 3 times x, or x ln of 3. ln of 3 times 1, or just ln of 3 is equal to 11 over 7. Okay, let's see what we got here. I want to solve for x. So this x is what I want to get to. So let's subtract ln of 3 from both sides. Everybody okay with this one then? Subtracting ln of 3 from both sides. Alright, dividing through by ln of 3 now on both sides, get that x by itself. So on there, so finally got x equals ln of 11 sevenths minus ln of 3 divided by ln of 3. Whew, alright, you calculator people, all yours. Can you punch that in? And can you get something that's very close to a negative 0.59? Lots of parentheses there. Really careful where you put in those parentheses. Negative 0.59 should be, as you punch it in. Carefully as you punch it in.
I got negative.
What was it?
0.548.
Okay, let's see.
Yeah.
So here's the way I would punch it in. First of all, because you see how you have two terms on top, you need to start it already with a parenthesis on top because you want to hold that whole entire numerator by itself. So here's what I got. I got a parenthesis starting off before I do anything else. ln of 11 over 7, close off that parenthesis to close off the ln. Minus ln of 3, close off that parenthesis to close off the ln, and then close off the whole entire numerator. We good? The denominator, you don't need an extra parenthesis because there's only one term there. So negative 0.59 is good. And again, not an equal sign here. It's almost like a little jagged equal sign. And that means approximately negative 0.59. Okay, we're good there. So what we do is we really put in the ln markers on both sides. Power rule says I can multiply out the x plus 5 or any exponent, and from then I work my way up to get to solve for x. Good there? Alright, one little problem. What happens if you have x on both sides and they're both stuck inside the exponent? That's my problem. And then the bases are 3 and 2. There's no way I can make the bases the same here. Alright, here we go. If you are still sticking with me here, again, base of 3, base of 2, no way I can put bases together. So let's stick in a ln on both sides. Ln of 3 to the x plus 1, ln of 2 to the 2x. And so yeah, so we work it on both sides now at the same time. Cool. Multiply the x plus 1 out as the multiplier times ln of 3. This one we're going to take out the 2x, put in front of ln of 2. Okay, kind of careful here so you don't get lost with where the x's should be. That's the problem here. Distribute the distribute the ln to the x, so x ln 3 plus ln 3. So now we got to think about the x. Where do you want the x? What should you move in order to get x by itself? Yeah, I think I'm going to do that too. Yeah, I'm going to subtract x ln of 3. I'm going to move everything over to the other side here. So 2x ln of 2 subtract x ln 3. Good there? So all the x's got pushed off to the right-hand side. Alright, next. Almost heard you, George? Not yet. If I heard you say factor, then yes. So I got this x over here, I got this x over here, so let's factor out an x. Because that will allow us x now to be a multiplication of something here. So how about 2 ln of 2 minus ln 3. Good there? Factoring out the x. Now we have ourselves what we want to divide by. So divide by 2 ln 2 minus ln 3. So now we have ourselves ln of 3 on top. 2 ln of 2 minus ln of 3. And once again, punch it in a calculator, see what you get. Anybody with an answer approximation to an answer? Let's go with the answer here. So punching in a calculator here, be careful. On top, you don't need extra parentheses, but on the bottom, now you need those extra parentheses to keep your denominator together as one piece. So ln of 3 on top divided by, again, start a parenthesis first. It's 2 ln of 2 minus ln of 3 and extra parentheses on the bottom. So those of you that do not have a calculator with you, I would suggest go home today and kind of punch in these things to make sure you get them the same exact answer as we're getting them here. All right, so I got approximately 3.82 is what you should get. All right, next one. It's kind of weird. It's called exponential equations in quadratic form. This would be kind of a bit of a weird one here. Is again, look at an example here first. All right, let me do this here. Sorry, because that looks like a weird example here. Let me jump to this one first, and then we'll jump to the more difficult one here. So I got e to the 2x minus 4, e to the x minus 5 equals 0. All right, you guys will run into these here. All right, one little thing here I guess we should mention. Is notice it kind of looks like a quadratic equation a little bit here. Notice you have this little 2x over here, then you have the x, and then you have nothing. So e to the 2x, you got e to the x, and then constant term. All right, what we're going to do is we're going to sort of play with this constant term, but you got to think about this here just for a little bit. E to the 2x, this little piece right here. Tell me if you guys agree here, what I'm going to do on the side here. So e to the 2x, isn't that really the same thing as e to the x squared as well? Would that give you the same thing as 2x? So once you write it like that, then you can kind of see like, oh, hold on, I get it. It's just like this. So e to the x squared minus 4 e to the x minus 5 is equal to 0. Okay, and if that's the case, here's what we're going to do. We're going to do something called substitution. Sometimes it's u substitution, sometimes it's y substitution, just depending which book you're using. Your book uses y substitution, so we'll do that. So notice real quick the middle term right here, e to the x. If you square it, it'll give you e to the x squared right here. So here's what we're going to substitute that middle term. If that's the case, tell me if you guys agree here. 1 second, let me do something here. This becomes y squared minus 4y minus 5 equals 0. Agreed, disagreed? Hey, that's quadratic now. I could solve that. I've been doing it since at least a long time. Two numbers, multiply negative 5, sorry, add to negative 4. I'll go with that. Positive 1, negative 5. Cool. Split them into two different pieces. And solve each of those guys. Becomes y is equal to negative 1. and y equals 5. The only problem is we're not solving for y, we're solving for x. So what we do is we back substitute the e to the x in. So now we have e to the x is equal to -1. E to the x is equal to a 5. So technically what we're going to do is we're going to solve for x. All right, how do we do this? Hey, there's an e over here, so kind of carefully, whenever you see an e, what you want to substitute in is ln this time. All right, and you learned from previously that ln and e, they will cancel each other out. They are exact inverses of each other. But before we go on here, can you punch this in on the calculator? What's ln of -1? There isn't any. It goes right? So remember for exponential functions, exponential functions do this, right? They go like that if you read 4.1. So they go through 0, 1. But -1 is all the way down here. Here's your -1. Will these two lines ever cross? No. I don't think so. So this one gives you no solution. But the other one here, when does e to the x equal 5? We're going to do the same thing. ln e to the x on one side and ln of 5 on the other. L and E cancel each other out. And there it is. I did find an answer. For this answer, for this to be a factorable solution, and the solution is x is equal to ln of 5. Cool, cool. Okay, sometimes what happens is you'll have like e to the -x. And how do you deal with the ones that have -x in the problem itself? So here's what we've got to realize here. Off to the side here, let's see. What happens if you had a problem that looked like this? E to the -x. Doesn't that really mean you have this? A negative exponents means you take it to the reciprocal, or take it to the denominator. And so we have one sort of like that we've got to deal with here. So here's the one that I wanted to do. So can we solve this equation? Three to the x minus 8 times x to the negative, those are 3 to the -x, is equal to 2. Okay, the work is in front of you here, but I just want to clarify a few things here. This is an example from the textbook here, but again, again, 3 to the -x just means that you have this somewhere, right? And so what we do is we multiply by this number here everywhere. So multiply both sides. All right, if you do that, you get 3 to the 2x minus, and now this is going to go away completely because they're going to undo each other's work. This you get 2 times 3x. All right, that went away. That becomes a 1 because 3 to the 0 power is a 1. This gets scooted into the other side now. And so we have this. And it tells you what kind of u substitution you should make. All right, so can you finish it off? Let me make the appropriate u substitution. Let's see if you guys agree. This would be y squared minus 2y minus 8. Everybody agreed there? All right, next slide, see if this makes sense here. So you get y squared minus 2y minus 8, factors down into y plus 2y minus 4. Solve each of those, so you get a y is equal to negative 2. Other side is y is equal to 4, and then we're going to back substitute that 3 to the x in. And again, same exact scenario happens that happened last time. 3 to the x, it goes like this, right? It goes like this. Will it ever be a negative 2? Not possible. This one is possible. 3 to the x.
Are any negative numbers possible?
Not for exponential functions. Exponential functions have to be higher than 0. This one's possible. So can you solve for me 3 to the x equal to 4? Can you solve that one for me? What would x be?
And then 1.38.
1.262. All right, let me show the answers as we go this way here. So 3 to the x is equal to 4. Now, if you just use common log, you still should be the same answer. But you have to put log to both sides. And then this whole, there it is again. I could take the exponent, take it out in front, divide through by ln of 3. So real quick here, anybody just punch that in just to make sure you get the same thing? All right, with that, where's the stuff used at? Everywhere. But one place is population growth models. So this one right here is a population. This is population at the start of something. 1 plus r usually is your rate of population growth. And then you have time, how much time you want to invest. So usually this is done more for a population of people. You could also do it for any kind of population. Population of bacteria, population of viruses in a certain given sequence. The only thing is with exponential functions, you know that they're not going to always go like this, right? They're not going to go forever, right? And so exponential functions are really more part of a different part where they're called logistics functions. Here they go like this. For a time it'll look like an exponential function, and then it'll level off eventually. Cool. Okay, so population growth, earthquake models, I mean, you name it. There's a lot of stuff, applications of log functions. Statistics has a whole bunch of log ln functions in it. You don't see it sort of behind the scenes here, but they're there. Okay, so far we've been dealing with exponential functions here. So let's switch gears and let's go start solving logarithmic functions. So when you already have, at the start of it, you already have a log function in it. Okay, I'm going to give you sort of maybe like one of each type so we see it, and then we'll see if we have any time for other things. I still want to get to the inequalities here, so like a little bit of a push here to get there. Practice problem number 6. I need to solve this. So it's 1 plus 2 ln of x is equal to 4. All right, let's go for it here. So first things first, probably subtract 1 from both sides gives you a 3. Then from here, probably divide through by 2 everywhere, so it gets you 3 over 2. And here we are stuck. We actually want to get rid of the ln this time. How do we do that? We can do it one of two ways. So you could either put an e on both sides of the equation, and this time you're going to set the ln inside the exponent. Why do we do it? Because e and ln will undo each other's work. They're opposite functions here. So what happens is they really cancel each other out, and done. The other way to do it is just to change forms. And again, you guys looked at changing forms in 4.2. So we say, what's the base over here? The base is e. What's the exponent? 3 over 2. And what's the number? The number is x. So it's base, exponent equal to number. And you sort of change forms again. Look at 4.2 if you're not sure what I just did. Otherwise, you can just put in e on both sides of these here. If you did that, those two will cancel, and you're really left with the same thing. So you can put in the base that you want to undo the base that you have.
Is the e supposed to equal the number?
E is approximately 2.71828. It's kind of like pi. Pi is
So we
about
have to
3.14.
calculate, e 3 over 2, yeah.
Mhm.
Into
Yep.
the calculator?
Yep, you got it. Now on the answer key, on the answers to your homework, sometimes they'll want you to put the exact answer. This would be an exact answer.
On the
Sometimes,
test, would it be like that, or will we have to use the calculator in order to get the
except
answer?
for the calculator. The question is, when will we ever need this here? 47 and 48 on the test. There's 2 of them that you will need a calculator, and you give me answers in 3 decimal places. So it'll be something like that. Otherwise, there's some other solving equations, right? Let me see. Numbers 37, 38, and 39. Those are going to give me the exact answer because you don't have a calculator to solve. And then number 29, solve the logarithmic equation. Again, choose one of the answers, but in that case, you won't need a calculator for those. Okay, one little extra thing we got to do with logs that we don't have to do anytime else is when you get your answer, you got to make sure that this number is a positive. Not so much the answer itself, but if you're to plug it back in, you can only take logs of positive numbers. That's it. You can't take log of negative numbers. Can't even take log of 0. So you got to just make sure. We'll work on those in just a bit here. But you got, when you plug it back into the original equation, you got to always be taking the logs of positive numbers here. Okay. So yeah, you can kind of tell this is an exponential function. Exponential functions are always positive. In this case, you're done here. All right, let's go for it here. So practice problem number 7. Let's jump to that one. All right, what happens if you have 2 logs here? Something about expanded form and condensed form. Something we start off in 4.3. That's why they're so connected. All right, because the little plus sign. Hey, got two logs here. There's a log base 3 here, log base 3 here. Plus sign means what? What do we do if we want to put these guys together in condensed form? Multiply. So log base 3 of x squared minus 8x. Everybody okay with the multiplication there? It's this times this. And multiplied it out. Okay, in this case, you want to change forms. And again, you guys looked at that 4.2. 4.2. This is a logarithmic form. I want to change this into exponential form. So you guys tell me, what's my base? Ah, you read 4.2, right? My base is 3. It's the base on the log. So notice what's happening here. The x is stuck inside this log function. We want to get it outside of the log function. This is, we're going to do change of form. Change of form is going to log notation into exponential notation. So we take, what's the base? 3. What's my exponent? 2. Remember this? This is the exponent, goes over here. And what's my number? Awesome. Notice, voila, we've taken out of from inside the log function. I think we can solve this now, is that right? 3 squared? Nine. To George it's 17. Everybody else in the world is 9. Okay, subtract 9 from both sides, set it equal to 0, and I think we can finish this off here. Two numbers multiply to -9, add to -8. X minus 9, x plus 1, I go with that. Set each of them equal to 0, and solve, so I got myself x equals 9 and x equals -1. Okay, here's where we got to do the checking. So, can't take logs of a negative number. It doesn't make sense, especially when you look at a graph of a log function. So if I plug in a 9 back into my original equation, is there ever a time that I'm taking a log of a negative number? 9 minus 8, that's a positive one. Still taking, that's not, okay. And then over here, just the 9 itself, log of 9, that's okay. 9 is good. -1 plugged in here. -1 subtract 8. Oh, problem. So okay, if you can't be a log of a negative number, and the reason for it, they discussed that in 4.2, but here's the quick rationale for it. Exponential functions, they go like this. Exponential functions never touch 0 here. A log function is the inverse of a exponential function, so log functions go like this. So notice on this end, there's no such thing as a log of 0. There's logs of positive numbers, yes. And log of 1 will always be equal to 0. And again, have to read 4.2 for kind of a little deeper explanation on that. But I got myself x equals 9 as my answer. Okay, why is this one possible? Why do we change forms? Because one side had a log to it, the other one didn't. So I go from log form into exponential form to get the variables from inside the log function. Cool? Okay, got it. One more for you. And then we'll go on to inequalities here. What happens if you have log on both sides? right, let's put it into condensed form here. Let's see on the left-hand side, ln of x plus 5 plus ln of x plus 1. I'm going to write it as ln of x plus 5 times x plus 1. And if you can multiply that out real quick here, I'm going to FOIL that out. All right, how about ln of, let's see, x times x squared. X times 1 is x, 5x, so 6x, and 5 times 1 is 5. So there's my trinomial. Everybody good there? Okay, but notice we have ln of both sides this time. Ln of both sides. Hey, you know what? Isn't that mean that we have the same base, in a sense, from algebra? I have a base of e over here. I got a base of e over there. I can drop the bases. By dropping the bases, all I'm really doing is doing this. Voila, how easy is that? The ln's really just disappear. I'm technically dropped both bases of e. Alright, subtract x from both sides, add 1 to both sides. Hey, kind of flips it around. That's kind of funny. Now it's x squared plus 5x plus 6. Cool. Can you factor it and solve? Then go back to make sure you're taking logs of positive numbers. Okay, so hopefully we factored them down into a 2 and a 3. And set each of them equal to 0 and solved. You get x equals -2 and x equals -3. Okay, when you plug it back in to the original, do you ever take a ln of a negative number?
Only if you want the wrong answer.
Ah, okay. Or no answer at all, because it comes out to be an error. So -2, especially over here when you're subtracting. -2 subtract 1, that's going to be -3. I don't think so. -3 subtract 1 will get -4. ln -4, I don't think so. Oh, bummer. So in this case, no solution. None of them worked at all. Okay, good there. And again, some fun stuff if you have the opportunity to read through example number 9. They're kind of fun little things. This is really a logistics function right here. That's what it looks like. So it's made to model behavior that sort of goes like this. Starts low, there's an increase for a while, and then it starts flattening out. If you kind of think about it, like cell phone sales. Cell phone sales sort of do this here. They start off for a while, they're humongous, and then slowly they taper off as more and more people have it, or at least the consumers that are ready to buy have it. So, example number 9, if you wanted to see it here, but I really want to get to, before we are done, I want to get to inequalities, because those we need to see. Ding, ding, ding. So let's do an example problem here, then we'll try one ourselves here. Or two. Alright, example problem here. Let's go for it here. Solving inequalities involving exponential expressions. This is from the textbook. This is example number 10. I'm going to look at it, and then I'm going to set up another problem very similar to it. So in this case, let's see what I have. I'm going to solve this. Here's my inequality. I'm going to solve it for x eventually. And there's one little quick little thing you got to think about here. When do you have to switch the inequality? When you're dividing by a negative, or when you're multiplying by a negative, okay? Okay, so let's go for it here. So as we're trying to solve for x, we go here, we subtract 3 from both sides gives us 15. We divide by 5, gives us 3. Are we okay here so far? Okay, and here's a little problem. This x is stuck in the exponent. And so what we do is we put ln on both sides. Or log, whichever one you like. So what does that allow us to do? It allows us to take this x and put it out in front. There it is. And so I'm ready to solve for x. I'm going to divide through by ln of 0.7. Now real quick here on your calculators, punch in ln of 0.7. Oh, cool. It's negative. Is that right? Okay. Here's what we should have seen in 4.2. Anytime you take a log, this is an ln function or log function, whatever you say, whatever you want it to be. So log of 1 is going to be 0. Log of anything that's less than 1 is always going to be a negative because of this little curve right here. So where it touches 0 is at 1 right here. So ln of 1 is 0, but ln of 5, it's a negative. ln of 7, ln of 0.7, it's negative. ln of 1.3, so what do you guys say? Positive or negative? Hey, it's positive, right? It's past the 1. That's all we're looking for. It's past the 1, we know it's positive. So in this case, when we do divide through by ln of 0.7, what's the problem here? It's a negative number. So when we do this, we have to switch our inequality. So there's a switching of the inequality. And kind of funny, when you punch it in a calculator, ln of 3, that's a positive number, divided by ln of 0.7 gets you a negative number at the end. So you know that one of them had to be negative. Cool, so kind of careful there. You got to switch the inequality around. So ln of anything less than 1 is a negative number. Or ln of anything between 0 and 1 is a negative number. Okay, easy one for you guys to try. All yours here. Watch my time here. So I got 10 minutes. Okay, that would be just about right. Okay, so notice these are exponential expressions, right? X is in the exponent, and then we'll switch gears to a log expression. So 3 times 0.5 to the x plus 7 greater than 19. All right, let me try it here. So I'm going to subtract 7 from both sides. I'm going to divide by 3, and I get 0.5 to the x is greater than 4. Everybody good so far there? And again, that x stuck in the exponent. Let's put ln to both sides. Take the x, put it on front, so now I got x times ln of 0.5 is greater than ln of 4. Divide through by ln of 0.5, and voila. Don't forget, I have to switch the inequality. All right, anybody got what is ln of 4 divided by ln of 0.5? Ah, cool. It's exactly -2. Cool. So the answer is x is less than -2.
Mr. H?
Yes.
Why do we switch the sign again? Why do we flip it?
Sure. Because ln of 0.5, if you punch that into a calculator, you should get yourself a negative number. So technically what we're doing is we're dividing through by a negative number on both sides of inequality. Kind of like same thing if you did something like this. Come on. In a sense, what we just did this right here on both sides.
It's only negative when you put it in the calculator.
No. You know it's negative because this guy is less than 1.
Oh,
So if that is less than 1, then you got yourself a negative number. Okay, good there. So there's the exponential inequalities here. Let's jump through last one here called the logarithmic inequalities here. How to solve this. Alright, we got ourselves a little problem with logs. Remember that whole issue, you can't take log of a negative number? Actually, you can't take log even of 0. You have to only take log of positive numbers. So, we have to deal with domain first. The domain for log of 2x minus 5, got to deal with this guy first. And so I ask myself, when does 2x minus 5 is greater than 0? So I have to solve this before I start solving the inequality. So I add 5 to both sides, I divide by 2, and there it is. So for the domain to work, x has to be greater than 5 halves. Good there? So again, this is for the domain, because log functions have a domain problem. Okay, next, now let's start solving the problem itself. So let's keep this in back of our heads here real quick here. Now let's solve the problem itself. To get rid of the logs, what we do is we put in a base that's going to get rid of the logs for us. So put in a base of 10 here, base of 10 here, and the log in the exponent is going to cancel with the base of 10. Done. So go to here. Okay, then we go with, let's see, adding 5 to both sides, divided by 2, so we got this right here. And what we have to do is we have to combine this. And if you want, maybe the easier way to combine it is just by graphing this guy here. When are both of them true at the same time? That's your question. It's an AND statement. So x is greater than 5 halves. That's what, 2.5? 5 halves is here. That means it goes this way. That's for my domain. That's for my domain issue. Okay, now let's look at our solving issue. X is less than or equal to 15 halves. That's 7.5. So over here there should be a bracket now. That's 15 halves. And now this one goes this way. So now, where are both of them true at the same time? It's just that set in the middle. Do they always bunch up in the middle? No, not necessarily. They may be going both to the right hand side or both to the left hand side. It doesn't matter. Okay, we good there? So one final problem here. So let's try our hand in this. ln is now the log. 1 minus 3x is what is inside the log, and we've got to figure out when is this guy greater than 2. All right, let me do at least the part of it here. So the domain issue. For domain, 1 minus 3x has to be greater than 0. If that's the case, we subtract 1 from both sides, divide through by 3, and tell me if you guys agree, x has to be less than 1/3.
When doing the domain, is it always going to be less than?
No. You start off as saying this inside of this has to be greater than 0, and then you keep on doing the work. The only time it changes is because it's a -3. If this was a +3, then it would not have changed, and it would have been x greater than 1/3.
So you'll always make it greater than?
Uh-huh. Cool. All right, now let's solve the problem itself. ln of 1 minus 3x greater than 2. We got a little problem because this is not log. You can't put a base of 10. You do that only for logs. And the reason why we did that last time, because there's no number by the log, so that means you do have a base of 10. What's ln? A base of? E. So let's put in an e on both sides then. So the ln goes into the exponent, and this just cancels off completely. So now left with 1 minus 3x is greater than e to the 2. All right, let's keep on working here. Let's see, I'm going to subtract 1 from both sides. That means it'll give you e to the second minus 1. Divide through by -3. Okay, here it goes, dividing through by -3. I got to switch the inequality around again. So that means it's going to be switching inequality. And let's see, negative goes out in front if you like. You can have it like this, where the negative just sort of sits out in front of the fraction. Or you can have it so that the negative sort of comes into the top. So negative e squared and a plus 1. So 1 minus e cubed, squared over 3. Either or is fine. You get the same answer anyways. But now we got a little problem. First of all, I see both inequalities facing the same direction. That's my first problem. Then I don't even know what in the world is 1 minus e to the squared divided by 2. What is that even approximately? I know 1/3. 1/3 is about 0.333. So can anyone just check for me what is 1 minus e squared divided by 3? Careful, make sure you put an extra set of parentheses for the numerator, because that is all one piece. Awesome. Okay, cool. Punching in the calculator should give you about -2.129685366. Okay, so at least now I know. So let me start my graph again. So that means 1/3 is about right here. It goes that way to the left, is that right? To the left, right? Right? To the left, right? Okay, the other one. This is going to be around -2.13 or so. So 1 minus e squared over 3. And that's going to go, again, it's a parenthesis and it goes off to the left. So now the question is, were both true at the same time?
Yes.
Just this one here, huh? So this one then becomes the final answer. Right there. If it was higher than the 1/3, then just be x is less than 1/3. That would be the answer. We good there?